Thanks, Anthony. Hi, thanks for coming. I'm going to talk to you about what we do at Planet Labs. I'll give you a general introduction about us as a company, some of the data that we're collecting from our satellites, and then I'll tell you about what my team is doing in particular to build mosaic maps of the Earth every day. So, first of all, the mission of Planet Labs as a company is to image the whole Earth every day, making change visible, accessible, and actionable. So that is our sort of one-line slogan. The way that we have gone about implementing this is to design, build, launch, and operate our own satellites for Earth imaging to take pictures of the surface of the Earth, aiming towards daily coverage. So here is one of our spacecraft. This is actually much larger than actual size. It's only 30 centimeters, about a foot long, right? So 30 centimeters by 10 centimeters by 10 centimeters. And has solar panels that fold out. Beyond that, this is our main constellation of satellites. These are called doves. We call them doves that do the bulk of our imaging. We also operate some other satellites that came from another company that is now part of the Planet, which is called the Rapid Eye satellites. We have 5 Rapid Eye satellites that are similar resolution, a little bit larger satellites. Also have an archive that goes back to 2009, so that's useful for going back farther in time. But I'm mostly going to be talking about the data that we get from the Dove spacecraft. Okay, so this is a snapshot of our doves in orbit over the surface of the Earth. This is before the most recent launch that I'll talk about in a minute here. You can see if you look at these various orbits, there are 2 basic families of orbits. There's this one big sine wave that goes sort of through Canada and Northern Europe down to here, right? So these are the orbit of the International Space Station. That has an inclination of about 52 degrees north and south. Those satellites were launched to the space station and deployed out of the space station, and they're in nearby orbits now, gradually spreading themselves away from the space station itself, but in orbits of the same inclination. The other family of orbits are the really high inclination ones. You see 2 different ones, one coming down like this and one going up like that. And those are the sun-synchronous orbit satellites. So those have an inclination of about 82 degrees. So they image everything up to 82, very near the pole, north and south. And they also have a once per day orbit well, sorry, it's not once per day, but it's one, it precesses at the same rate as the rotation of the Earth, so that we're imaging every strip at approximately the same time, solar time every day. So we get much more consistent imagery as we get these strips, one after another, with the same lighting conditions and the same time of day. So those satellites, let's see, so these OE14, OE20 are the most recent, prior to the previous launch, satellites that are doing that. There's 12 of those. We just launched another set, thank you, that is going to be in a similar orbit, and those will all have very consistent characteristics to those. All right, so this is a heat map showing the number of images we have. It's a little bit out of date, but you can sort of extrapolate this forward in time since October. Here we have repeats of, stacks up to 128 deep of images, and these are especially at the at the inclination of the space station orbits, about 52 degrees. So you see the high repeats near that inclination, and we see lower coverage north of that. This is before we had very many of the satellites in high inclination orbit. That's going to increase with time. It's going to become much more spatially uniform and fill out the poles in terms of coverage. All right, but this is the basic framework of what we're talking about, the raw imagery we have to work with. In terms of area imaged over time, this is the history of all of planets' dove data. So in these dove constellations, how many square kilometers are we collecting per day? We only had a few satellites in orbit in early, well, I guess late 2015, early 2016. Let's see. Here's 2015, January 2016. So a few in orbit in 2014. Another launch in mid 2015, late 2015 here, and then a couple more launches. Each of these is a launch event where we get more satellites in orbit. The Flock 2P, this marks the first group of 12 high inclination sun synchronous satellites. You can see that boosted our area covered once those satellites were operational and spaced out in their orbits. We're, by the beginning of this year, acquiring 50 million square kilometers per day of imagery. So how much is 50 million square kilometers compared to the surface of the Earth? It's about a third. Right? So we're, as of now, imaging about a third of the Earth daily. These are now joined by the most recent launch. This was last week, right? Yeah, so last week. It was Valentine's Day here in the US, February 15th in India. The Indian PSLV vehicle launched 104 satellites into orbit, the largest number of satellites ever launched at once. 88 of them were ours. They were all deployed successfully. We're communicating with all of them. I'm going to show a quick video. This is actually a video of the whole launch taken from on board. I'm going to skip ahead. For the rocket part's cool, but I want to show the deployment part here. About there. There we go. Okay. All right. So the main satellite cargo has been deployed now. This is the deployment of the doves. This is looking from the top stage of the rocket as our satellites are ejected from their deployment containers. So here they go, just shooting by one after another, gently tumbling. They have no propulsion. They're just in free fall now, so they're each in their independent orbit. There we go. You can see these are front-lit, overexposed, but you can see they have the front panel open and the communications antenna pointing forward. The solar panels haven't yet deployed. Right. So 88 of these coming out like this. What's a success rate? So for launches, we've had in the history of the company about 12 successful launches, I think, right around then, and 2 failures. We've had relatively few on-orbit failures once they've deployed. So they have some lifetime and various components degrade and so on. But in general, once they get to this stage, they're pretty likely to be successful. So it's a launch that's the trickiest part. So launches have a fairly high failure rate, even today. Still coming, right? More of these being deployed. So 88 of these, the largest private constellation of satellites ever. So all gently tumbling. So over the next few weeks and months, we're going to be, the first task is to detumble them, to stop their gentle rotation so they can orient themselves, communicate with the Earth. We're in contact with all of them already, and then we will commission the optics and start taking images of the Earth and getting them back. So we've already got a few pictures back from the first one, and we'll be getting more over time. Reaction wheels. So we have orientation control. Yep. So we've got full control over orientation. We can point anywhere we want. We just can't boost the orbit, and we can't change the orbit. I say we do have one ability to change the orbit, and that's differential drag. So even though we're in orbit above most of the atmosphere, there's a very thin residual layer of the atmosphere out at this altitude, which is just over 500 kilometers. And by orienting the solar panels, we can put our satellites in low drag mode or high drag mode, depending on the direction they're facing. And we use that to space out the satellites intentionally to get the maximum dispersion of a particular orbit. So over months, we'll increase the spacing, and we'll get them as dispersed as possible. Right now, they're pretty tightly clustered from whatever residual momentum they had being popped out of the deployment canisters. Okay, so the images we're taking, everything is from these satellites is in the visible, red, green, blue, and the near infrared. So just out past the red part of the visible spectrum. So we have those 4 bands of imagery. They're taken in individual takes. You can see 1 frame, 2, 3, 4, 5 frames in the visible and 5 frames in the infrared that should overlay on top of each other. They're actually taken with the same sensor with different filters on the top and bottom half. So we take a shot of the visible and the near infrared at the same time, and then we stitch them back together later. The ground resolution is between 3 and 5 meters, depending on the exact orbit they're in. Typically, 4 meters is what you can expect for that most recent deployment, those satellites in the sun-synchronous orbit. So most of it is about 4-meter ground resolution. Okay, so now let me just show a couple examples of recent things we've seen in the images. So you may have heard about the Oroville Dam in California. This is a dam. This picture was taken last fall, so this is September. And let's see, yeah, there we go. The shoreline here and the water line, you can see the water level is pretty low, right? This was after 2 years of California drought. And there we go, this is working. This is after the failure of the main spillway last week. So the main spillway had been damaged. They had to reduce the amount of flow coming out the main spillway, and eventually this reservoir, after the recent rains in California, overtopped the dam and spilled over the emergency spillway here, and there was some fear that this would eventually give way. Actually, I think the fear was a collapse of the main spillway, but it was intended by design to overtop here. That seems to have been contained. It's still raining in California, but this reservoir is crested again and seems to be intact still. But you can see the damage here and all the vegetation that was eroded. Oh, no. Oh, no, that doesn't work. There we go. So if you look at the vegetation there, oh, there's, well, yeah, there. That. Here. Oh, and there. All right. I'll show you another example in the near infrared. So this is a black and white image that's just showing infrared data. This is in the Tibetan Himalayas, fairly steep glacier topography, and last fall, this glacier collapsed, and this is a debris flow that happened over a very short period of time. So this is essentially an ice avalanche, right? That there was a total failure of this glacier slope, and it ran downhill and outward a distance of 10 or 15 kilometers. So there. Okay, if we have time, I'll show you a few more images at the end. But what I'd like to spend most of my time on in this talk is what my team does at Planet Labs, and that's building mosaics. So what we do is to take all of these images that are taken over time, all over the Earth, and stitch them together in a seamless way so that we build maps out of them. So you may have seen Google Maps and other web map tools. We build a layer like that out of all of our imagery, stitching them together so that it looks like one coherent whole. Google Maps, for example, takes imagery from many different sources. They have aerial images, high-resolution satellite images, low-resolution satellite images, from many sources, and they may come from many times. So what we're looking to do is take the data that we're collecting and show it in discrete time slices to show differences from one to another and how things change with time. So first of all, in case you're wondering how hard this problem is, this is a picture of the Earth, right? A satellite image of the Earth. This is the next generation blue marble image from NASA. So this was generated in 2004 from MODIS data from NASA satellites, remote sensing satellites at about 500-meter resolution. So this is what the Earth looks like from space, right? So there's a lot of processing that goes into this. What does the Earth really look like from space? It's more like this, right? This is a picture from Monday so February, Northern Hemisphere winter, clouds through most of the Northern Hemisphere. So how many images did we get today of the Earth? Well, there's some pictures in North America. You can see the Great Lakes. You can see the Midwest. You can see North Africa. But, bits of South America, not much of Europe. India. But there's a lot of coverage. So on average, more than 50% of the land area of the Earth has clouds, right? Some of them we can see through and around. There are clearings here and there. If you look at the Amazon, it looks cloudy, but there's also a lot of green in between the clouds, right? So we do get images that give you pictures of the ground, or at least the tree canopy in the Amazon every day. But they might not be the same trees every day, right? They're little popcorn clouds that move from day to day. So we're going to take images and combine them one day with the next and take the best ones. And at 500-meter resolution, that's the difference between averaging this over, say, a month time span to get this, right? So this is sort of the state of the art for doing this for MODIS data at 500-meter resolution. Google Earth does similar things with all sorts of different data. We're doing this with our 4-meter resolution PlanetScope data everywhere on Earth. So I'll talk a little bit about how we do that. So there's a few components to this. We have, as I mentioned, individual snapshots, essentially scenes that we take that are like snapshots from a camera passing over a strip of the Earth. So before we get to this, we have to rectify it. We have to locate it exactly on the surface of the Earth. And we have to project it into a standard projection. I'm not going to talk about those steps, but those are important ones that we have automated at Planet. I'm going to talk about what happens after we've done that. How do we take those images that already have been rectified and turn them into a seamless mosaic? So let's say we've got 25 images that intersect this particular square on the Earth. So I take a tile that has dimensions about 20 kilometers across, 20 kilometers high. And I look at every image we've got that intersects that tile. So let's say we've got these, I guess it's 30 images, well, 6 by 6, 36 images that intersect this tile. They intersect in more or less random orientations in different ways. So we've got all of these different image chips that intersect, say, this part of the tile, that part of the tile, this part of the tile. Some of them are higher quality, some of them are lower quality, some of them might have clouds, some of them might have haze, some are from older sensors that didn't work as well as the latest sensors that we have. So we're going to select by various metrics, cloud cover being the most important. We definitely want the cloud-free image that's taken that day. The sharpness of the image. So we have metrics that tell us, how well are we resolving the actual ground there. That may be due to the optics of the satellite, the altitude of the satellite, but more likely it's due to hazy conditions on the Earth, that the image isn't very sharp because the on-the-ground conditions are hazy. We might have images with different sun angle, different sensors. We might have images that are taken at different times. Maybe we're interested in the most recent images, so we might put a time metric that we're weighting more heavily towards recent imagery than older imagery, or we want a particular seasonal target, so we want the date that most closely approximates a summer scene, so we'll penalize scenes that are out of that in time. So take all those, we choose the best scenes, and we stitch them together to build that tile. So in this case, we only need really 3 scenes. Say that's the best one. This is the second best. And then there's one chip here in the bottom corner I didn't show that we'll get from the third best remaining scene. And we've fully covered all the pixels in our tile. So let's say for this particular tile, it only took 3 scenes to do this. So an average number for the tile size we use, which is 2,000 pixels by 2,000 pixels, and that's about, we're doing this at about 4.7 meter resolution at the equator on a standard web tiling grid. So on average, we're selecting about 6 scenes that will complete that tile out of all the ones that might be possible for there. For a global mosaic, there are about 4 million tiles on the Earth. There's also some overlap between neighboring tiles. Some scenes will be shared between neighboring scenes. So we have something on the order of 20 million tiles, 20 million input scenes that would go into creating a global mosaic. So these have all been selected and stitched together. There's 2 more steps we have to do to make this a seamless mosaic. One is called color balancing. So these scenes all come off the camera, sometimes with different cameras, with different satellites, different filters on the cameras. So there's some variation in that. With good calibration, we should be able to correct for that, and for the most part we do. So the bigger difference is the atmospheric conditions. So this is an example from a province in China where I haven't done any color correction. I'm just using the standard calibrated color curves for each input satellite. And we can see the various swaths of different satellites. I've done the same scene selection I showed in the previous image, but we see some are darker, some are lighter, some are kind of pink, some are kind of green. That's differences in atmospheric conditions at different times. So it's hazier or less hazy. It is a very hazy region of China. So almost entirely differences in atmospheric corrections. So we want to get from there to this, right? So that all the colors look the same. So formally, if we're doing this calibration from the images we actually take in space to what things should look like on the ground, that's a radiometric normalization. We want to know what is the actual reflectance that's being returned by something on the ground. So you need to do a full atmospheric correction for how things are passing through the atmosphere. And there are ways to model that with more information. We're going to do a slightly different way where we're going to normalize things essentially by eye, by the visual characteristics of the data. And the easiest way to do that is called, we call it CDF matching. It's the cumulative distribution function. It's essentially taking the integrated histogram and putting the input data into the form of a color target. So this is an image I got from MacBox, a blog post that they use the same technique for some of their things. So here's a source image. So this greenish image at the top left, the reference image that we're matching is the center one. You can see that it's more pink tinted than green tinted. We want to take the image on the left, make it look like the image in the center, and then the result is the one on the right. So how do we do that? It's a pretty easy mapping of the distribution of the red, green, and blue pixels in that image. So the middle row is the histogram. The cumulative distribution function, the integrated histogram, is the blue here. And we want to match it to the reference one, which is this green, well, the green and red dashed line. And basically, it's just filling in the bins in each red, green, blue pixel, and the lowest 1% will go into this bin, the next 1% will go into the next bin, and so on. You just fill up the bins until they match. And that, if the images are similar enough, works really well. It doesn't work everywhere. So what happens if you have snow in the image and your color target that you're matching colors to doesn't? Well, then you're going to force the output image to have the color distribution of the color target, even if it isn't right. So here's an example. Sorry, I don't have the color target example here, but the way we do it with planet images, we build a color target out of Landsat data. We match that histogram of Landsat data for a particular area with our input imagery. Here we had brown input scene from the Landsat, and we took data that had snow in it from PlanetScope, and it just turned all the snow brown, right? So histogram matching is not a very smart method. It's just going to give you out what you told it to do. So it matched those colors. We gave it brown, so it gave us brown. We're working now on a new method which does a more intelligent parametric fit. So we don't match the full shape of the histogram, but we have parametrized shapes. And you can think of this as like curves in Photoshop. If you, have done any photographic retouching where you're bringing up the tones and making things more vibrant in Photoshop, by using smooth curves, you're not going to distort things too far. You can increase them or decrease them, but you're not going to force things into a pattern that they're not. So by using curves that are parameterized, and this is essentially by a linear fit in the red, green, and blue, plus a nonlinear overall gamma curve, we can properly match snow in the valleys and brown in the mountains in this case, right? So that's the idea of doing a more parametric fit. So that improves our result in the case where the input scene doesn't look like the color target. That's particularly important because we're especially interested in things that change on the ground. And we want to be able to see that change instead of to mask the change by putting it through the blender. All right, so now we've normalized the color after we've selected the scenes. There's one more thing we have to do. We're taking these different image chips, and we want to stitch them together. Whoop, there we go. We want to stitch them together, and we need to remove the scene edges. So here we have 3 different scenes, and you can see the boundaries between those scenes. So we use a technique for gradient blending to remove those scenes. Essentially, we solve a partial differential equation where we set a boundary condition that we're going to allow things to move along the seam lines, but we're going to constrain them to hold their shape as much as possible inside the seams. By solving that equation, we get the smoothest possible integration of those 3 scenes, and the seam lines go away. So this technique works really well in general, and we rarely see seams in the final product. Okay, so the slide I skipped here, this is our global color target. All right, so this is the input that we're going to use to match a particular mosaic. This version happens to be global summer, so this is chosen Landsat data so that we have summer data in the northern hemisphere and in the southern hemisphere, right? So we've got, say, typically July data in the northern hemisphere, typically January data in the southern hemisphere. We allow some time span around that and a wider time range at the equator in the tropics where things change less. And we cover the entire Earth with a Landsat surface reflectance mosaic at that resolution. So this is just an intermediate product for us, building the mosaic that's going to determine the final color of our individual scenes. There. This is our mosaic. I filled in the oceans. We don't actually have imagery over the entire ocean, so I've filled in a blue background in the oceans, but everything over land here is PlanetScope imagery. You can see the few places that we don't have covered over land, like Greenland is just shaded relief gray. Right, so everywhere that there's color imagery is actually PlanetScope imagery. This is our global summer base map, so our current best view of all of our PlanetScope data. We're also generating seasonal mosaics for other seasons. We're working on doing fall, and eventually we'll do all of the northern hemisphere seasons as well as the global summer version. Okay, so this is sort of our best of all time mosaic right now, and we'll continue to update these seasonally as we go. Just zooming in on one area in Chicago in the mosaic. Let me talk about the next step, though. What's really interesting, once we can do this and once we're getting data more frequently, is building up the time domain. So now, we're not just building one mosaic for all time, a static mosaic that's just going to live. We're going to start doing time slices. So the first step in doing that is monthly. So here are monthly global mosaics, only data strictly within each month, starting January 2016, running through January 2017. So this is actually a 13-month repeat here. So it's kind of a stuttered 1 year. So we see a repeat of January. So you see the increase in data rate. Another interesting thing, January 2017 back to January 2016, you see the drop in coverage. That is looking backwards at the increase in our data rate. This is what we're getting now, January, and then last January, right? So you see it stepping up in time. So July, August, September, we're into our the full operation of our current constellation before the most recent launch of 88 satellites. And then you see another drop-off that's seasonal with low sun angles and cloudier weather in the northern hemisphere in late fall and the winter. Okay, so now this is the start of our time machine. We're going to look at what does the Earth look like at a particular point in time. So we can do monthly, and we have coverage of 80 to 90% of the Earth monthly now, and that's going to be increasing. The next step is to go to weekly. So here I've just done California, and this is weekly California. I didn't label it, but it's on a repeat from about May through early December of last year. So you can see it looks a little bit random, and there are actually cycles depending on the orbits of the International Space Station, where you have more coverage and less coverage from that particular orbit, and the sun synchronous orbits are a little more uniform. You can see those are the swaths that have orientation like this are all sun synchronous. The ones that are like this or like this are in ISS orbits. So we're getting more of our data in sun synchronous orbit. And now this weekly mosaic is around 50% there for California by the end of the year. And now we're going to be imaging 3 times as much, so we will get nearly complete coverage over the world weekly soon. So that is the next step. How do we do this daily? The first step is weekly time slices. Like I just showed you, we're computing now monthly routinely. By the end of this month, we'll be this next month, about a month from now, we'll be computing weekly global snapshots routinely. That's not different in any material way. It's just using the increased data rate and sampling it at a higher frequency. As we get more data, it will be more filled out. But then how do we scale that up to daily? So that is the next interesting question that we're going to have to tackle. If we're getting imagery of the whole Earth every day, or at least the whole cloud-free portion of the Earth every day, how do we reflect that in a current mosaic? So how do we turn that into a mosaic where a map where you can see what is the most recent image we have of every place on Earth? So that's our goal. And the way that we plan to achieve that this year is with a freshest on top mosaic. That we're going to have an updating mosaic that will be updated at least once a day, and probably more like hourly. That every time we get a new batch of images in, we'll update all of the mosaic tiles that those images, which cross some quality threshold for being cloud-free and other quality metrics, so that those mosaic tiles are updated to the most recent image. Same thing's going to happen an hour later. We'll update the map so it's always up to date. There's some questions. Are we going to store snapshots of those every day? Certainly we'll have the weekly snapshots, but there are computational and storage costs associated with all of those. So there are trade-offs, but certainly we will have one view of the freshest on top mosaic that's going to reflect all of the highest quality imagery that we're getting every day. And now that we have the satellites in place to do that, we don't see any obstacles in being able to expose that to everyone. All right, so I've shown you a lot of examples. So you might wonder, how you can actually take a look at the things we do in more detail. So the first and easiest thing you can do is look at our website and our gallery. So www.planet.com/gallery. We have examples of our imagery from all over the world, all different times, back through our archive. Everything that's in the gallery is licensed for Creative Commons by SA, which means you can pretty much do anything with it as long as you give us attribution and you release it under the same license. Right, so that's one way you can access these images. If you stop me after the talk, I can give you a business card. I've got examples of all these on my business cards that we go back, and we post them in our office as well. All right, here I'm going to do a quick demo of our Imagery Tool, and this is available to customers and partners. Yeah, okay. There. All right. Okay, so let's say we want to look at Seattle. There's the city of Seattle. I want to see, let's turn this off. I want to see what images of Seattle we have, say, this week. Okay, so February 17th. So that's, what, Friday? It's been a little cloudy, but Friday we got some images. Now let's look up here. All right, so there's campus. Right. Yeah, so you can see we're looking through the haze a little bit, but there's a picture of campus on last week. Look back into January. We have a different image. Just picking some of the sharper images we see, the less cloud-free or the more cloud-free.
5-meter resolution.
Yeah, approximately 3 to 5, between 3 and 5. Well, this view is limited to the tile, so the actual pixels are 5 meters now, but I can't over zoom to give you a full view of it. But, yeah, but you can see you're resolving individual buildings that are, 20 meters across or something like that, 30 meters across. All right, and then if you look down at the bottom, you see the histogram of images over the in Seattle. So you see, through 2015 we have a fairly low level, and then the second half of last year it increases, and more images in the last couple of months. All right, well, I should wrap up here, so let me skip back. North Korea, well, we have that too. Oh, no, that's North Carolina. Sorry, wrong one. Yeah, there we go. All right, North Korea. It's a big country, so we need to zoom to actually get individual images. We have to look at a particular place. So let me get an area of interest. Well, that's not the main thing we're doing, but all right. So yeah, so there's some imagery from North Korea in a particular location, say. Yep. So all of this is global. Let me actually show one. Let me clear this. Clear. I guess while I'm here, I can show that the global view is of the mosaics here. So the same time-lapse mosaics of monthly slices are available in this view. Here we have monthly and quarterly. That's the axis on the bottom there. So if I want to go first quarter of this year, second quarter of this year, third quarter of this year. So those are all mosaic views, and then I can drill down to monthly, October, November, December, and then eventually that will go to weekly, right? So it'll be the same. Right. All right. Okay. So let me skip back. Okay, let me show you another more in-depth way to have access to data. We have a partnership program with academics and nonprofits. So if you're interested in a particular project that could use these data, and you're interested in working with it directly, you can apply on our website and get into this program to have access to our data for up to 6 months for a particular project, and then we could negotiate longer terms for longer collaborations than that. But we're working with academics in various fields, doing glacial monitoring and deforestation projects and other things around the world. Oh, I guess I'm about done. One last thing, we're also hiring. So we are still a growing company. We're looking for people who do, we're looking for engineers, for data scientists, machine learning experts, and software engineers, front end and back end. And we just opened an office in Bellevue. So our main office is in San Francisco, but we're especially interested in expanding at the Bellevue office just across the lake here. So if you're interested in any of those things, take a look at our careers page, and feel free to contact me. All right, so let me wrap up there. If you have any questions, here's my email and my Twitter handle, and I'm happy to stick around a little while to answer any questions you might have. Thanks. Yeah. Yeah, okay. I'll repeat the question for the microphone. The question is, other companies are spending hundreds of $millions on high-resolution satellites. How did we settle on 3 to 5 meter resolution? The early on focus of our company was to do things on an axis that no one else is doing it, and that was time. So by exploiting the small, cheap satellites and have a lot of them, what we can get is a time repeat that's unmatched, and that's what we're aiming for in the daily repeat data. So yes, there are other ways to get high-resolution data, and I guess it was in the news about 2 weeks ago that we are actually getting into the high-resolution data game by acquiring the satellite division of Google, now called Terabella, which was formerly known as Skybox. So they operate better than 1 meter resolution satellites. But with sort of similar philosophy, a lower cost than those traditionally, hundreds of millions of dollars or billion-dollar satellites for remote sensing. So that is a good fit and a next step for us to get into high resolution. And I didn't talk about it at all in this talk, but having the monitoring at medium resolution, at 3 to 5 meter resolution, having the high resolution at the same, that's targetable in the same company gives us the opportunity to use medium resolution change detection to cue acquisition of high resolution imagery. So that's one of the things we're really excited about doing in the future, is taking the temporal resolution that we have in this constellation and augmenting it and using it to help target the high resolution assets. Yep.
Perhaps a competitive advantage that those people have over you guys is the large amount of computational infrastructure they can leverage for real-time image processing. What
Yeah.
kind of information can you give us about what sort of computational infrastructure you guys leverage?
Yeah. Okay, so the question is about our computational infrastructure. So all of our computation is using those same cloud services, right? So we use the large cloud providers to do various things. So all the storage, all the computation, So yeah, I think we can scale in that same class. Yeah. In the back.
So I didn't quite understand your calibration. You want to look for new things that are happening, and yet you're using old images, to make your fitting and so forth.
Yeah.
I didn't quite get it.
Okay. Well, so first of all, what I was talking about is the visual mosaics. So if you're doing a change detection, you might want to work with the analytic data that's standardized to radians, for an individual location. A lot of what I'm doing here in the mosaics is trying to make things look good. So not necessarily the most principled way to calibrate a sensor, but the way to standardize the images so they look like a coherent whole. So we're modeling what the surface of the Earth looks like in a general sense, but maybe not in a very principled way, right? Yeah. Yeah.
What's the timeline between the satellite takes a picture and the images?
Yeah, that's a good question. What's the timeline from acquisition to availability of imagery? So most of that latency is on orbit. So the time between snapping a picture and downlinking it can vary. Typically, it's hours, can be days, depending on prioritization. And then once it's downlinked, once it's in our system, it's fully available. There's some hours, a small number of hours latency typically. Yeah, I think what I've seen is the median time from acquisition to pipeline is something like 8 or 9 hours. So all the way through. Yeah, back. How long does the satellite stay in orbit? Our standard, I believe, is to have orbits that will decay in less than 10 years. In practice, all of the orbits that we use are quite a bit less than that. The space station orbits are less than 2 years typically, so we start losing them in about 18 months. The Sunsync ones are a bit longer, maybe about 5-year lifetime, something like that. Our design lifetime is 5 years. We expect the components to last longer than that on average, but you might expect them to be in orbit for another 5 years. Yeah. Yeah.
So you said that you kind of skip over the oceans.
Yeah.
Is that because of lack of features or
Yeah. Yeah. So the question is, why do we skip over the oceans? There's a couple reasons. One is data limitations, that we prioritize land over ocean. So we don't typically image over open ocean, that we do near shore. Another is, even if we do take images of the ocean, and we do get quite a few, we don't have ground control to rectify them, to locate them precisely. So there's higher uncertainty in those. There is still some interest in some of those images, though. So I won't say we don't have any, but we don't prioritize taking ocean imagery in general. Yeah.
Yeah, so for the gradient mapping of stitching images, do you worry about differences in shadows?
Yeah, that's a good question. So do we worry about differences in shadows? The gradient matching isn't the biggest problem with that. It actually does pretty well, just solving that as a boundary condition. So it's not too jarring. It's more, you just see the discrete jump of shadows going this way and shadows going that way. It's an issue. One thing we don't have that you see in a lot of satellite imagery is look angle. So you see geometric things where a satellite's taking very far off nadir. So some satellites might take as far as 30 degrees, look angle off of straight down. And when they take that image, they have to orthorectify that as if you were looking at it straight up. And then you get distortions of buildings that look like they're sort of sideways like this. Our images are almost always directly nadir, so very small angles. So we don't see that kind of geometric effects. But we do get some of the lighting. And now in Sunsync orbit, that's very minimal. It's mostly the International Space Station orbits that see the huge changes in shadows. Yeah. Yeah.
So in your products, do you have daily snapshots?
Do we have daily snapshots? Not yet. So that's what I'm talking about. That we expect to have this year is the daily snapshot of the Earth. Right now, you can get daily images, so you can search for a particular area and get those images in that place, but not the entire Earth. Yeah. Yep.
Is there any plans to offer like an open source version, maybe like David or?
Yeah, that's a good question. No specific plans, but we would definitely like to be able to get our data out to more people. So we're exploring ways to do that. I would say one program we have is for ambassadors for joining our public data sets is Open California. So we do have open data for California already. There's still a little bit of a sign-up hurdle, but it is CC licensed once you have access to it. So you can redistribute it and use it for anything you want, essentially. I guess we should probably wrap up here. We're running out of time. Yeah.
Kelsey, thanks again for
All right, thank you.